skip lecture 4 and 5.
So today we are going to cover the topic zener diode and these objectives. Become familiar with the analysis of and the range of applications for zener diode. So what is zener diode? Okay, when the reverse bias on a crystal diode is increased, a critical voltage called breakdown voltage is reached where the reverse current increases sharply to a high value. That things we know from the diode VI characteristic curve, right? Now, the breakdown region is the knee of the reverse characteristic as shown in the figure. Look at over here. This is the knee, okay? As shown in this figure. The satisfactory explanation of this breakdown of the junction was first given by the American scientist C. Zener. Therefore, the breakdown voltage is sometimes called zener voltage, and the sudden increase in current is known as zener current. So the great scientist, by his name, okay, the name came, okay, zener diode. So this is the diode characteristic curve. Okay, this is the forward bias region. This is the reverse bias region. And look at over here. At some point, this is the breakdown point. Reverse characteristic, okay, current increases sharply. Okay, and we symbolize it by this. So the breakdown or zener voltage depends upon the amount of doping. If the diode is heavily doped, depletion layer will be thin, and consequently the breakdown of the junction will occur at a lower reverse voltage. On the other hand, a lightly doped diode has a higher breakdown voltage. When an ordinary crystal diode is properly doped so that it has a sharp breakdown voltage, it's called a zener diode. Okay, so this is the main point for zener diode. Okay, when an ordinary crystal diode is properly doped so that it has a sharp breakdown voltage, it is called a zener diode. A properly doped crystal diode which has a sharp breakdown voltage is known as a zener diode. It may be seen that it is just like an ordinary diode except that the bar is turned into jet shape. Look at over here. This is ordinary diode symbol, but the bar over here it has been turned into a jet shape for the zener diode. Okay, so this is the symbol of zener diode. The following points may be noted about the zener diode. A zener diode is like an ordinary diode except that it is properly doped so as to have a sharp breakdown voltage. A zener diode is always reverse connected. Okay, keep in mind when you use a zener diode, it's always reverse connected. That is, it is always reverse biased. That's a working condition of zener diode. Okay, or it's always reverse biased. A zener diode has a sharp breakdown voltage called the zener voltage Vz. When forward biased, its characteristics are just like of ordinary diode. The zener diode is not immediately burnt just because it has entered in the breakdown region. As long as the external circuit connected to the zener diode limits the diode current to less than the burnout value, the diode will not burn out. Okay. So what is the equivalent circuit of a zener diode? The analysis of circuits using zener diodes can be made quite easily by replacing the zener diode by its equivalent circuit. What is the on state? Two state I will consider. What's the one is the on state, other is the off state. During the on state, when the reverse voltage across the zener diode is equal or more than the breakdown voltage Vz, the current increases very sharply. In this region, the curve is almost vertical. Look at over here. I think if you use this picture, I think it will be can be explained more clearly. You see, when we apply the voltage, this is the zener voltage breakdown for VZ. Okay, when the voltage is less than VZ, reverse voltage is less than VZ, then that's the off state. The circuit will be disconnected. Okay, off state. The circuit is disconnected. Okay, off state. But when the voltage reverse reaches VZ or more, then at the point of VZ you get the sharp breakdown. Okay, and diode will be in the on state. So when the diode is on state, what we can do, we can replace for our analysis this diode with the equivalent voltage VZ. So let's continue. So when reverse voltage across the zener diode is equal to or more than the breakdown voltage VZ, the current increases very sharply. In this region, the curve is almost vertical. It means that voltage across zener diode is constant at VZ even though the current through it changes. Therefore, in the breakdown region, an ideal zener diode can be represented by a battery voltage VZ as shown in figure. Under such condition, the zener diode is said to be on the on state. Look at over here. So at that point, when the zener diode is on, we can replace this zener diode with the equivalent voltage VZ. Okay, so this is the equivalent circuit of zener for on state, and at that situation, V greater than or equal to VZ. So this is the on state. And what is off state? When the reverse voltage across the zener diode is less than VZ, but greater than 0 volt. Less than V is less than VZ, but greater than 0 volt. Okay, the zener diode is in the off state. Under such condition, the zener diode can be represented by an open circuit as shown in the figure. So during the off state, we can use an open circuit to represent the zener diode off state. And this is the condition: V greater than 0 volt and V less than zener voltage VZ. So that's the off state. So that's the main application of zener diode as voltage stabilizer. So how it works? A zener diode can be used as a voltage regulator to provide a constant voltage from a source whose voltage may vary over sufficient range. Suppose you have a source and it is voltage is varying, but even though the voltage is varying, source is varying, by the zener diode we can get a constant voltage. So it can be used as a voltage regulator. The circuit arrangement shown in the figure. Look at over here. This is the circuit arrangement. This is your applied voltage source EI. This is the zener diode. This is your load resistance, and this is the series resistance R. Okay. Actually, when the fact is like that, in case of zener diode, that's a very interesting fact. Okay. Suppose this voltage is fluctuating, varying. Okay. Let's say this zener voltage, let's say for example 20 volt. Let's say this source is sometimes 20, sometimes 21, 22, 23, 30 volt. Okay, even though you get constant voltage 20 volt at this point across the load. How? The extra voltage that more voltage that is fluctuating over here. Okay, that should be that energy is absorbed in this load. So by using this technique, it's maintaining a constant voltage source. Okay, so let's explain more details. The zener diode of zener voltage VZ is reverse connected across the load RL, across which constant output is desired. Okay, so we desire a constant output across this load. Okay, across this load we desire a constant output. It will always remain fixed even though this source varies. The series resistance R absorbs the output voltage fluctuation so as to maintain constant voltage across the load. So this resistor R absorbs the fluctuation. Okay. So to maintain the constant voltage across the load. it may be noted that the zener will maintain a constant voltage Vz or equal to E0, okay, across the load so long as the input voltage does not fall below Vz. So that's the one point to keep in note, that you see the input voltage should not fall below Vz. Okay, then you can maintain this constant voltage across the load Vz or equal to EO, output voltage. This output voltage will remain constant. Okay, make sure this EI should not fall below zener voltage Vz. Can go up, okay, but extra fluctuation, those energy comes from extra fluctuation will be absorbed by this arm. When the circuit is properly designed, the load voltage E0 remains essentially constant, equal to Vz, even though the input voltage EI and the load resistance RL may vary over a wide range. Okay, so in case of your practical situation, sometimes the load resistance can vary. This is source voltage can vary over a wide range, even though the applied voltage across the load will remain fixed. So, zener diode can be used as voltage stabilizer, and it's widely used, okay, in practical application. Now, case one, in this situation, okay, suppose the input voltage increases since the zener is in the breakdown region. The zener diode is equivalent to a battery Vz as shown in figure 2. Okay, so look at over here. So we can replace the zener diode with the equivalent voltage Vz for our ease of analysis. It is clear that output voltage remains constant at Vz equal to E0. The excess voltage is dropped across the series resistance R. Okay? This will cause an increase in the value of total current I. The zener will conduct the increase of current I while the load current remains constant. Okay? Hence, the output voltage E0 remains constant irrespective of the changes in the input voltage EI. Another case, now suppose that the input voltage is constant. In previous case, we have used, let's say, input voltage was variable. In this case now, consider input voltage is constant, but the load resistance RL decreases. This will cause an increase in load current. If the resistance decrease, current will get increased, right? So this will cause an increase in load current. The extra current cannot come from the source because drop in R, and hence source current I. So will not change as the zener within its regulatory range. So this will cause an increase in load current if load resistance get decreased. The extra current cannot come from the source because drop in R will not change as the zener is within its regulatory range. The additional load current will come from a decrease in zener current IZ. Okay. Consequently, the output voltage stays at constant value. So this is the analysis over here. Voltage drop across the R. You see the resistance are EI minus E0. Put over here. The voltage drop across this resistance are EI minus, if you consider this circuit, outer circuit, okay, the drop across this resistance R is EI minus the drop across the load E0. Okay. Current through R. Okay. If you look at the circuit again, this is the current through I. This is the current I. Okay. And I equal to IL plus IZ. Okay. IL plus IZ. Kirchhoff's current law. If you look at the point, apply Kirchhoff's current law. This I is equal to IL plus IZ. Okay. Applying Ohm's law, we have R equal to EI minus E0, R by I equal to resistance Okay, this is Ohm's law. Okay, apply the Ohm's law. R equal to V by I. So, this is the voltage drop across the load, and this is the total current. So this is the value of the R. So we want to solve Diode circuit. The analysis of Diode circuits is quite similar to that applied to the analysis of semiconductor diodes. The first step is to determine the state of zener diode, that is whether the zener is in the on or state or off state. Next, the zener is replaced by its appropriate model. Finally, the unknown quantities are determined from the resulting circuit. So this is the zener diode example that we are going to analyze first. Let me take you to the textbook. This is your textbook. Okay. So look at the network. The network for figure 2.110 is designed to limit the voltage to 20 volt during the positive portion of the applied voltage and 0 volt for the negative excursion of the applied voltage. Check this operation and plot the waveform of the voltage across the system for the applied signal. Assume the system has a very high input resistance, so it will not affect the behavior of the network. So look over here. This is the input voltage Vi you are applying to the system network. This is the resistance R. This is the zener diode Vz equal to 20 volt in this case. You see, you want to limit the voltage to 20 volt. So zener diode has the rating 20 volt. Okay, zener voltage 20 volt. And this is the one of the silicon diode, and this is the system. For positive applied voltage less than zener potential of 20 volt, the zener diode will be in its approximate open circuit state. As we have seen from our analysis, when the voltage across the zener diode is less than Vz, the zener diode is open circuit. Okay, and the input signal will simply distribute itself across the elements, with the majority going to the system because it has such a high resistance level. Once the voltage across the zener diode reaches 20 volt, the zener diode will turn on. Okay, look at over here. When you have the applied voltage Vi, you are increasing the Vi less than 20 volt, it is off state. Voltage is increasing 20 volt and more, the diode will be on, and it will maintain a constant 20 volt because it is zener diode. Okay, so when the voltage, this input voltage will be 20 or more, this will have a constant 20 volt. Okay, so the voltage across the system will lock in at 20 volt. Okay, so look at over here. Vi greater than 20 volt. Okay, because there's a silicon diode, so it has a 0.07 voltage drop. So you need to add it. Okay, Vi greater than 20.7 volt. This voltage plus this voltage. Got over here. Further increase in the applied voltage will simply appear across the series resistor with the voltage across the system and the forward bias diode remaining fixed at 24 and 0.7 volt respectively. The voltage across the system is fixed at 20 volt. Okay, as shown in the figure, because look at over here. This is 20 volt because 0.7 volt of the diode is not between the defined output terminal. This 0.7 volt, this silicon diode is not in the output terminal, so it will be locked at 20 volt. The system is therefore safe from any further increase in applied voltage. For the negative region of the applied signal, okay, for the negative region of the applied signal, the silicon diode is reverse biased and it is open circuit and presents an open circuit to the series combination element. The result is that the full negatively applied signal will appear across the open circuited diode and the negative voltage across the system locked at 0 volt. Okay. as shown in the figure. See? So this negative part on the negative side, this cycle, the entire voltage, you see, the this entire input voltage will appear across this open circuit diode, and the 0 volt will appear over here. Okay, sir. Okay. So if you plot, you see, you get this output. This is the V output. This is the Vi, and this is the V out across the system. The use of the zener diode as a regulator is so common that three conditions surrounding the analysis of the zener diode regulator are considered. The analysis provides an excellent opportunity to become better acquainted with the response of the zener diode to different operating conditions. The basic configuration appears in this figure. This is the basic configuration. This is the series resistance R with the input voltage source. This is the zener diode, and this is the load resistance R. Okay, this is the basic configuration. The analysis is first for fixed quantities, followed by a fixed supply voltage and a variable load, and finally a fixed load and a variable supply. So first, consider this situation. Vi and are fixed quantity. Input voltage is fixed and resistance, load resistance is fixed. Okay, fixed quantity. The simplest of zener diode regulator networks appears in this figure. The applied DC voltage is fixed, as is the load resistance. So input voltage is fixed, load resistance RL is fixed. The analysis can fundamentally be broken down into two steps. First step, determine the state of the zener diode by removing it from the network and calculating the voltage across the resulting open circuit. So first step, remove the zener diode, okay, from the network and calculate the voltage across the resulting open circuit. What voltage appears across the load. So applying step 1 to the network results in the network like this. Okay, so it is open circuit, remove the zener diode. So how an application of the voltage divider rule results in V, this voltage V that appears across the open circuit is equal to VL, right? V is equal to load voltage VL. And what is VL? If we apply the Ohm's, if we apply the law, Kirchhoff's voltage law, okay?
Voltage divided law.
Yes, across this load. Kirchhoff's voltage law across this one. Across this one. Across the intercircuit. Okay, across the intercircuit. Kirchhoff's voltage law. Okay. So this is you can write. I think this is V equal to IR. Okay. VI plus R plus RL. This input VI divided by R plus RL is the total current I. This portion. Okay. This portion. VI divided by R plus RL. Okay. This portion is the, I think, total current. This portion. If I highlight, this portion represent I. This portion represent current I. Okay. This portion represent current I across the load. That circulate. So this I multiplied by load resistance RL. Total current multiplied by the RL is the voltage drop. V equal to IR. Simple way, V equal to IR. So we can correct this the R and this the total current. So this is the voltage across the load. If V greater than Vz, the zener diode is on and the approximate equivalent model can be substituted. If V less than Vz, the diode is off and the open circuit equivalent is substituted. Okay, so When the diode is off, open circuit model will be substituted. Otherwise, we'll use the approximate model. So step 2, substitute the appropriate equivalent circuit and the solve for the desired network. Desired unknown. Okay, we have done the open circuit situation. Okay, now substitute the appropriate equivalent circuit and solve for the desired unknowns. So for the figure, when the diode is on, we can replace this zener diode with the equivalent zener voltage. So we have replaced the zener diode with the equivalent zener voltage when the diode is on. So at that situation, okay, at that situation, this load voltage is equal to the zener voltage Vz, fixed. Okay. So VL equal to load voltage VL equal to zener voltage Vz. The zener diode current must be determined by an application of Kirchhoff's current law. So look at over here, IR. This is the total current, okay, in the circuit IR plus this resistance equal to IZ plus IL. Okay, the current across through the zener diode and the current through the load. So how much current through the zener diode? IZ equal to this total current IR minus the load current IL. Where IL equal to VL by RL. Okay, this is the VL divided by RL. Load voltage divided by the load resistance. That's the load current. And IR equal to this IR equal to VR by R. Okay, VR by R. This the voltage drop across this resistance is VR divided by this resistance. Okay, VR by R. So what is VR? VR equal to this VI minus VL. Okay, Kirchhoff's voltage law. You see, you want to get the voltage across this R. So the VI equal to VR plus VL. So what is VR? VI minus VL. Okay, so this is the voltage drop across the resistance R. So what is the current? This drop divided by the resistance R. So this is the current through the resistance R, and this is the current through the load resistance. Okay, IL. The power dissipated by zener diode is determined by VI. Okay, this is the power dissipated by the zener diode Vz equal to Vz zener voltage and the current through the zener diode Iz. Okay, and there is written, make sure you see that must be less than PZM, maximum power dissipation allowed specified by the zener for the device. For every device, when you get the data sheet, it has a rating. Okay, this zener diode can support maximum this much power dissipation. That is the rating is PZM, M for maximum, and this is the power zener diode power dissipation. So this value must be less than maximum value. Otherwise, things will get burned out. Okay. Before continuing, okay, it is particularly important to realize that the first step was employed only to determine the state of the zener diode. If the zener diode is the on state, the voltage across the diode is not the V volt. When the system is turned on, zener diode will turn on as soon as the voltage across the zener diode is Vz volt. It will then lock in at this level and never reach the higher level of V volt. Okay, so make sure when the zener diode is on, it will get locked. Okay, and it will not change. So that's the analysis of our first example. Any question over here? I've understood.
Yes, sir.
Okay, now we can proceed to the next example. Okay, for the zener diode network of this year, okay, 2.115, determine VL. Okay, load voltage VR. This is VR. Voltage across this resistance R. IZ current through the zener diode and the zener power dissipation PZ. Repeat part A with RL equal to 3 kilo ohm. So first in case A, part A, our load resistance is 1.2 kilo ohm. Then we will repeat the entire process for the load resistance 3 kilo ohm. So already we know how to solve it. So let's just go with the solution. Following the suggested procedure, we redraw the network as shown in figure 2.116. Okay, look at over here. We redraw the network. Okay, first step, make it open circuit, off state. That means okay, voltage B equal to okay VL. So applying our equation, already we have derived the equation V equal to RL VI divided by R plus RL. So this is the voltage V. Okay. When you open circuit, okay, when you remove the off state situation, okay. So it is 8.73 volt off state situation. So since V equal to 8.73 volt is less than VJ 10 volt, the diode is in the off state as shown on the characteristics of figure 2.117. Look at here. At 8.73 volt, the diode is off state. VL equal to V 8.73 volt. Diode is off state. Substitute the open circuit equivalent results in the same network as in figure 2.116, where we found that V L equal to V equal to 8.73 volt. VR, so what is VR? Vi minus VR. This is VR, okay? Across this is VR. Let me just draw a small. This is VR. Across VR is across this R drop, okay? So this VR equal to Vi minus VL. So VR equal to Vi equal to 16 volt, and this VL equal to 8.73 we have calculated. So this the drop over here is 7.27 volt. Okay. And what is IZ? Since this open circuit, IZ equal to 0. And what is the power distribution? Since IZ equal to 0, power distribution was 0 watt. Okay. Now replace this zener that with equivalent voltage. Okay, when we apply voltage, Vj that means applying voltage is greater than or equal to Vj. Okay, so applying equation 2.16. Okay, repeat part A. Okay, with 3 kilo ohm. Okay, I think same thing we are doing, same analysis we are doing with 3 kilo ohm instead of 1.2 kilo ohm. Okay, same analysis. That means part A, we are doing the same analysis with 3 kilo ohm. Okay, just same analysis. So just replace instead of 1.2 kilo ohm, use 3 kilo ohm. So you get the voltage V, open circuit voltage V is 12 volt. And in this case is V equal to greater than 12 volt. Look at over here. As we are doing the same analysis, it will not be open circuit now. You see, we have changed the load. This is the interesting fact. We have changed the load. Due to the change of load, what happens? Okay, look at over here. That's the interesting fact. As you change the load from 1.2 kilo ohm to 3 kilo ohm, what is happening? The voltage across this load has been increased. So as you change the load resistance from 1.2 kilo ohm to 3 kilo ohm, That's the interesting fact. Okay, the voltage has been across the load has been increased from 8.73 volt to 12 volt. And what is the thing? 12 volt is greater than general voltage VJ 10 volt. So in this case, the diode is on. Since is V equal to 12 volt is greater than VJ 10 volt, the diode is in the on state. And the network of figure, this apply appears. So what we do? We replace that open circuit condition through equivalent general voltage. So as you increase the load, voltage this voltage VL has been increased to more than 10 volt, and the diode is on. So even though voltage has been increased more than 10 volt, if you look at over here, 12 volt, still it is maintaining 10 volt across the load. Extra voltage, extra voltage, extra power will get dissipated over here. Okay, look at over here. Since V equal to 12 volt is greater than VJ 10 volt, the diode is now on state and the network, this network results. So applying the equation, now VL equal to VZ equal to 10 volt, the constant voltage will be maintained. The drop across this resistance R equal to Vi minus VL, that is 16 volt minus 10 volt equal to 6 volt. It's 6 volt drop. And what is the load current? VL by R. VL equal to 10 volt divided by 3 kilo ohm, 3.33 milliampere. And what is the current through the resistance R? VR by R. Okay, what is VR? 6 volt drop across this. Okay, so divided by R into 1 kilo ohm. So this is the current to the R. Okay, 6 milliampere. And what is IZ? The current through the zener diode, IR minus IR. So this is total current IR minus the load current. You have found the load current is 3.33 milliampere. Okay, this is your load current. This is the load current, 33 milliampere IL, and this is your total current, 6 milliampere. No, this is not the load current. So this is the load current. This is the load current. Okay, and this is the current, total current. This is the total current. 6 milliampere is the total current. Okay, so total current minus 3.33. 6 milliampere minus 3.33 milliampere. So that's the current, 2.67 milliampere through the zener diode, IZ. So power dissipation, PZ equal to VZ IZ, VZ equal to 10 volt, and this is the current through the zener diode, 2.67 milliampere, 26.7 milliwatt. And for this diode, the maximum power dissipation is rated as 30 milliwatt, so it is less than 26.7 milliwatt. Okay, now fixed Vi and variable Rn. So in this situation, when the input voltage is fixed and load resistance get varied, due to the offset voltage Vz, there is a specific range of resistor values, and therefore load current will ensure that the zener is in the on state. So how you can vary, in what range you can vary the load resistance to maintain the zener voltage on state. So that's one consideration you need to make. Okay, what is the minimum value of the load resistance and what is the maximum value of the load resistance that you can use to keep the zener dot in the on state. So fixed Vi and variable RL. So what is the minimum value of RL and what is the maximum value of RL? Within the range, you can safely vary the load resistance to maintain the zener dot in the on state. So let's find the range, okay? So too small a load resistor RL will result in a voltage VL across the load resistor less than VZ, and the zener dot will be the off state. So to determine the minimum load resistance that will turn the zener dot on, simply calculate the value of RL that will result in a load voltage VL equal to VZ. Okay, so we want to first calculate what is the minimum safe value of load resistance. Okay, so that's the technique. So in this case, VL equal to VZ, and this is the VZ. Okay, R divided by I, VI divided by RL plus R. This is the current. I by R equal to R by, okay, Ri. Okay, this is R, and let me just highlight. This is the portion. This portion is your current. I. IR equal to voltage drop. So this is the I and R. Okay, solving for RL. So we can find that minimum value of RL equal to R VZ by VI minus VZ. And that's the situation. That's the situation you can consider to calculate the minimum safe load resistance. Okay. So this is the minimum value of load resistance that you can use. Any load resistance value greater than RL obtained from equation 22, okay, 2.20 will ensure that the zener dot is the on state. So you cannot go below this value. You can go up. And how much you can go? Okay, what is the maximum range you can go? Okay, so that's the we need to are interested. So in this case, in this situation, the diode can be replaced by its VZ source equivalent. Okay, the condition defined by equation 2.20 establishes the minimum RL, but in turn expresses the maximum IL as. Okay, so this is the IL maximum current through the zener diode. Okay, what's the maximum current? VL by RL. When the current is minimum, okay, when the current is minimum, okay, resistance is minimum. When the resistance is minimum, okay, you get the maximum current. Okay, so what is the minimum value of resistance? Load resistance that will safely keep the zener dot on. We have calculated from here. Safe value, minimum value. Okay, so when the resistance is minimum, current will be the maximum. When the current is maximum, VL will be VZ. Okay, when the diode is on. So we can tell that that's the maximum current when the resistance is minimum. So we have the minimum value. So this equation gives you the maximum current, load current. Okay. So the condition defined estimates the minimum RL, but in turn specifies the maximum load current. Once the diode is on state, the voltage across R remain fixed. Okay. VR equal to Vi minus Vz. Okay. This is the R. Remain fixed. Okay. On state, the voltage across the R remains fixed at VR equal to Vi minus Vz. Source voltage minus the zener voltage. And the IR remains fixed. IR equal to VR divided by R. This VR divided by R. So current remains fixed. IR total current remains fixed in the, okay. And the zener current IZ equal to total current minus load current. Okay. This is the total current minus the load current. So second IZ. Kirchhoff's current law. So since IZ is limiting to IZM, maximum zener current. So IZ is limited to IZM as provided on the data sheet. It does not affect the range of RL and therefore IL. Substituting IZM for IZ establishes the minimum IL as. Okay. So what is the minimum current through the zener diode? Equal to IR minus IZ maximum. Maximum current through the zener diode. Okay, this IZM comes from the data sheet. IZM as provided on the data sheet. So maximum current through the zener diode. So if you substitute the maximum current, that means subtract maximum current. Okay, this is the maximum. So when this is maximum, so if you subtract from this one, this current will be minimum. Okay, that means when the current through the zener diode is maximum, certainly current through the load will be the minimum. Okay, because uh, this IR equal to IZ plus IN. When this current through the zener diode is maximum, current through the load will be minimum. When the current through the load is minimum, you can calculate what is the maximum value of the load resistance. Okay, because as the resistance is increased, current will decrease. So when the current is minimum, you can calculate the maximum value of the load resistance. Okay, so maximum load resistance is RL max is VZ by ILN. Okay, zener voltage divided by the minimum current through the zener diode. So that's the maximum load resistance. So now we know what is the limit of load resistance. This is a limit. Minimum value. So this is the minimum value. This is the minimum value of load resistance, and this is the maximum value of our load resistance. So once you know the minimum and maximum value of load resistance, so within this range you can safely vary the load resistance, and it will keep the diode on. Zener diode on, the circuit will operate smoothly. Okay. So let's do the example. In this case, our source voltage is fixed, but we are varying the load resistance, and we know the range. Okay, this is our range. Two questions: minimum value and the maximum value. Within this range, it will operate as the circuit will be on. Okay, properly. It will operate properly. So for the network over here, 2.119, determine the range of RL and IL that will result in VRL being maintained at 10 volt. So what is the range of load resistance, minimum value and maximum value? And what is the range of load current, minimum and maximum current, that will make the circuit operational in the on state? That means the zener diode will operate properly at 10 volt. This voltage is fixed. Okay. So we want to know our limit of load resistance and load current, so that we can operate the circuit safely. And when we design the circuit, we will fix the limit. Okay. Yes, so determine the maximum wattage rating of the diode. So let's say to determine the value of RL, that will turn the zener diode on, apply the equation 2.20. So RL minimum 2.20. Look at over here. We have explained this one. 2. RL minimum. This is our equation. Okay. So replace the value. Okay. Look at over here. This is 1 kilo ohm. R equal to 1 kilo ohm. VZ is 10 volt. VI equal to 50 volt, and VZ equal to 10 volt. So it becomes minimum value of load resistance is 250 ohm. Okay, that's the minimum value. This is the minimum value, 250 ohm. Minimum. Okay. Voltage across the resistance R is then determined by the equation 2.22. By this equation, we then get the voltage 40 volt. voltage across the resistance R is 40 volts. Now equation 2.23 we calculate the current IR. Use the equation. Okay, current through the resistance R. VR by R 40 divided by 1 kilo ohm, 40 milliampere. The minimum level of IL is then given by the equation 2.25 by this equation. Okay, minimum value. Minimum value. This is our equation 2.25 IL minimum. Minimum load current. Okay, it counts IR minus IZM 40 milliampere minus 32 milliampere 8 milliampere. So this is the minimum load current that will keep the diode on. Okay, and with equation 2.26 determining the maximum value of RL. So this is the minimum value 250 ohm, and what is the maximum value? Use this equation 2.26. 1.25 kilo ohm. So a plot of BL versus RL appears in figure 2.1 to 128. Okay, it's the minimum value, maximum value. Within this range, the diode will be on state, zener diode. So if you know this value, then you can design a circuit. Okay, minimum load resistance will be 20 ohm, 250 ohm, and maximum value of the load resistance you can go 1.25 kilo ohm to maintain the circuit operate properly. So this is a range of load resistance, and a range of load current. Okay, 80 milliampere. Okay, 8 milliampere, 8 milliampere minimum current, and maximum current 40 milliampere.
Yes, sir.
40 milliampere maximum current. 40 milliampere you can go. Okay. So what is the maximum power dissipation? VZ, VI. Okay. This VZ equal to 10 volt. And what is the IZM? 32 milliampere. 30 milliampere comes from your, I think, data sheet. See? This is given in your data sheet. Okay. This value comes from your data sheet. This value come from your data sheet. These two value come from your data sheet. Okay. Data sheet. So we know the maximum power dissipation 32 milliampere. So what is the Pmax? 10 into 32 milliampere, 320 milliwatt. And the last situation, okay, that's the last situation, okay, where we keep the load resistance fixed, but we vary the input voltage Vi. Okay, so in this case, in this previous situation, we have varied the load resistance. Okay, now we'll keep the load resistance fixed and we'll vary the input voltage Vi. So in this analysis for fixed values of RL, load resistance is fixed. The voltage Vi must be sufficiently large to turn the zener diode on. The minimum turn on voltage Vi equal to Vi minimum, and is determined by VL equal to Vz equal to RL. This is the R by Ri. Okay, this I. This portion is I. Again, let me just highlight. This portion gives you I. Okay, so IR equal to Vz. So this is the minimum. Okay, minimum input voltage that will keep the diode turn on. So Vi minimum equal to just this is Vi minimum, this Vz into RL plus R divided by RL. Okay, from this equation just calculate Vi minimum. So the minimum turn on voltage Vi equal to Vi minimum. So this is the minimum turn on voltage. The maximum value of Vi is limited by the maximum general current IZM. Since IZM is equal to IR minus IL. Okay, IZM equal to IR minus IL. Kirchhoff's current law. Kirchhoff's current law. Okay, Kirchhoff's current law at this point. So IR max. Okay, maximum current through the resistors R. Maximum current through the zener diode plus the load current. Maximum value of Vi is limited by the maximum zener current IZ. Okay, so this is the key point to understand this case. If I just highlight it, the maximum value of Vi is limited by the maximum zener current IZ. Okay, since IZM equal to IR minus IL, so we can tell that maximum current through the load resistors, through the resistors are, okay, not load resistors, the resistors are equal to IZM plus IL. Since IL is fixed in this case because your resistance is fixed, in this situation, you see, it is fixed value of RL. Your resistance is fixed, okay? So IL also fixed because voltage is fixed, resistance is fixed. Load resistance is fixed, zener voltage that is fixed, okay? So load current is fixed. Since IL is fixed at Vz by RL, IZM is maximum value of IZ. The maximum Vi is defined by Vi max equal to Vr max plus Vz. This Vz is constant for zener diode. Okay. So what is the maximum voltage drop across this resistance? R. So if you know the maximum voltage drop across this resistance R is allowed because this is fixed, then you know what maximum value of Vi you can support. Because this will be this plus this. You know this is constant, fixed. So if you can calculate the maximum value of R, this value, okay, this maximum value you can calculate the max value, then you can know what is the maximum range of voltage source. So come over here. Okay, so this is the equation. So what is VR max? So we know what is VR max. Okay, VR max equal to R into IR max. Maximum IR. Okay, this current. When the current is maximum, then drop will be maximum to the resistance R. So when the current is maximum, drop across this resistance R will be maximum. So we know the maximum current from this equation 2.28. Okay, so this is the maximum current. This is the maximum current. So if you multiply the maximum current by the resistance R, then you get the maximum drop. So this is the maximum input voltage that you can allow. Maximum drop across the load, across the resistance R, not in the load. Okay. Maximum drop across the resistance R plus the zener voltage. So this is the maximum voltage that you can allow in your system. Maximum voltage. Okay. So determine the range of value of Vi that will maintain the zener diode in the on state. So using this analysis, now just we'll use the formula. This is our circuit, and we are interested in this input source. What's the minimum and what is the maximum of this source? Okay, minimum and maximum. So this is our resistance R, 220 ohm. And this is the zener voltage 20 volt, maximum zener current is 60 milliampere. Our load resistance is 1.2 kilo ohm. So just use the equation 2.27, this one, to calculate the minimum voltage. So just replace the value. You get minimum voltage is 23.67 volt. Okay. Now, what is the load current? Load current is fixed. VL by RL, load voltage divided by load resistance. VL equal to VZ because the diode is on, the diode is working properly on a state, 20 volt. It's 20 volt. And divided by load resistance 1.2 kilo ohm. That's given. Okay. So this is the load current that's fixed, 16.67 milliampere because the load is fixed over here. So what is the maximum current through the resistance R? Okay, IZM plus IN. Load current is fixed, and what is the maximum current through the zener diode? IZM. What is IZM? That is given, I think. IZM is given. IZM is given 60 milliampere. Maximum current through the zener diode. That is given. So this maximum value plus this IN. This gives the maximum current IR. Okay, so IR max equal to 60 milliampere plus 16.67 milliampere. That is the load current. Is the maximum current to the zener diode. 76.67 milliampere is the maximum current through the resistance R can be allowed. So what is VI max? Maximum drop across the resistance R plus the zener voltage. So this is the maximum current, and this is the resistance 0.22 kilo ohm, 0.22 kilo ohm. This is 0.22 kilo ohm. So this is the, if you just do the calculation, we get this is your maximum voltage that you can allow. So this is VI max. So minimum voltage for the source is 23.67 volt. Maximum source voltage you can allow 36.87 volt. So minimum 23.67 volt for the source and maximum 36.87 volt. Within this range, you get this 20 volt fixed output for the load.
Yes, sir.
If you go below or above, problem. Okay. That cannot operate at that range properly. So the input voltage source must within this range. Minimum value 23.67 volt in this situation, maximum value 36.87. Within this range, input source, the zener diode will be on the on state. That means it will give proper 20 volt output. Okay. So the results of this example reveal that the network of the figure with a fixed RL, the output voltage will remain fixed as 20 volt for a range of input voltage that extends from 23.67 volt to 36.87 volt. So in our analysis, we have calculated what is the minimum range of input voltage, minimum and maximum, what is the minimum and maximum range of the load resistance. So once we know the minimum and maximum value of the load and load resistance and the source voltage, we can safely design our circuit, and we can give the limit. Okay, maintain this limit. The source voltage cannot go beyond below above this range and below this range. The load resistance cannot fall below this value and cannot go up this value. Okay, so once you have this parameter, then give this parameter in your guideline, so that when people will operate with your circuit, they will follow those value, or you'll fix the value in your design. So that's all for zener data analysis. Okay, do you have any question? Calculation of minimum and maximum value, the source voltage and load resistance. That's very important. So that's all for the zener data analysis. Any question at this point?
No, sir.